So today we're going to be discussing about the derivative, which basically like the slope. Like say we have like in algebra, we'll assume you've learned this. So you have some function f, so x and f of x. So see we have 2 points. Hold on. So like this is say x, and this is some x plus h, right? So for the x-axis, we put that there, and hold on. And then we have f of x plus h, and f of x. So in algebra, you would have defined the slope. So like, so basically like, the slope is equal to, say, f of x plus h minus f of x over x plus h minus x. And see, those x just cancel out, so the slope is equal to f of x plus h minus f of x over h. So like this would just be just like the slope between these 2 points, which we call the line that basically like, if you were to like, the line that this creates is called the secant line. So basically the slope is defined as the slope, okay, not defined, that equals the slope of the secant line. So I'm just going to assume that I'll give you a few minutes to take notes. So I'm just going to assume that you've taken notes, so, or you could have paused the video, whatever. So we have this slope, right, which is equal to f of x plus h minus f of x of h. So what if we wanted to understand, so basically the difference between the derivative and the slope, so like say we have the derivative, you basically take the limit, so like this, so the notation for the derivative df dx is equal to the limit as h goes to 0. So kind of like the distance between x and x plus h. So like this distance here is h. Oh, let me just rub this off. So this distance here is h. So like basically we're making that distance go very, very small of f of x. So the definition of the derivative is basically f of x plus h minus f of x over h. So this could basically work for any function that is basically like differentiable at some certain point where it's continuous. So let's say we have the graph of 1 over x. 1 over x, x, which is basically like, oh crap, this is terrible. 1 minute. Whereas basically like when you take the derivative, it's basically like you can't take the derivative at point 0 because 1 over x is not defined at x equals 0. So it's not differentiable at that point. Oh well. Yeah, it's not differentiable at that point because you can't find the slope at that point simply because the function is not continuous at that point. So anyway, so this is basically just definition of a derivative. And let's try and apply it to some functions. So let's say we have f of x equals x squared. So basically, if you wanted to take the derivative of f with respect to x, that would be equal to the limit as h goes to 0 of, well, what is f of x plus h? Well, basically, f of x plus h would just be adding h to the input, so f of x plus h is equal to x plus h squared. So df dx would just be like, well, inputting the value for f of x plus h and f of x, that would just be x plus h squared minus x squared over h. So let's try and simplify this a bit. So using basically like the square of the binomial, right, is just equal to x squared plus 2xh plus h squared minus, and then all of this would just be minus x squared over h. And yeah, taking the limit as h goes to 0. So you can see these x squares just cancel out. And interestingly enough, these h's also cancel out. So basically, this is just equal to the limit as h goes to 0 of 2x plus h. And well, this is just 2x. So basically, like for any given point h, or well, there's precisely any given point x, you can find the derivative at that point, and it would just be equal to 2 times x. And also, the reason I brought up the function f of x plus h being equal to x squared, well, 1, because it's easy to do, and 2, because it's kind of like, it's gonna bring rise to this term called the power rule. Let me just rub all of this off. So basically so let's erase this together. The power rule. And that basically, like, if you were to take the derivative with respect to x of any given polynomial, or well, monomial in this case, of x to the n, it would just be equal to n times x to the n minus 1. And you can see, when we've taken the derivative, using the definition of the derivative, we have found that that rule kind of works for x squared, right? So like, when we've done the derivative, right, like we did for x squared, you notice that it was 2x. So that would just be like, let's say n equals 2, right? So meaning that we're taking the derivative with respect to x of x squared. And according to the power rule, this should theoretically be 2x to the 2 minus 1. And well, 2 minus 1 is just 1, so thus is 2x. And that is the same we've got for the definition of derivative, which is pretty cool. To me, at least. Well, whatever. This is basically just... So it kind of proves that the power rule kind of works, and we shouldn't have... And the reason why these type of rules exist is because, let's say, these rules exist because it's not going to be easy evaluating the limit over and over and over again. It's going to get tedious and kind of monotonous. Well, and also kind of hard to do. Because let's say we have, like, I don't know, sine of x over x. Like, what if we want to just use the definition of the derivative and take the limit as h goes to 0, and this would just be, well, times, well, if you were to add x to the input, it would be sine of x plus h over x minus sine of x over x over h, which seems a bit hard if you ask me, because it's not too easy to do. So anyway, it's kind of tedious. So I'm just gonna end it here with the power rule and all that. I can see this explanation is not gonna be too clear, but once we actually get into applying all this stuff, it'll get easier. So thanks for watching.